So hey everyone, I'm Luisa. I'm a PhD candidate at Swinburne University, and I'm also part of the AGA team, so I'm hoping you all paid attention to that, and you're all in love with UDGs from now on, because I'm going to build upon that. So let me start by telling you again what are ultra-diffuse galaxies. So these galaxies were rediscovered in 2015, and one of the most astonishing properties of them is that although they have the luminosities of dwarfs, they have the sizes of giants. So here is an image to scale of an ultra-diffuse galaxy, and you can see that it has a size similar to the Andromeda galaxy, but you can barely see it. And this is because it has a luminosity similar to a dwarf elliptical galaxy. Only by looking at this image, we can already start to think on ways these galaxies could be formed. They could have come from dwarfs, that something happened to them and was able to enlarge their sizes, and this is what we call a puffed-up dwarf scenario. Or they could have started their lifetimes as giant galaxies, but something happened that halted star formation right at the beginning. They didn't form enough stars and they didn't become what they were supposed to. And this is what we call a failed galaxy scenario. In terms of observations, we know, well, since 2015 until now, we haven't observed many UDGs, but the ones that we have, stellar populations, we know of at least two types of UDGs. In terms of ages, they can have intermediate ages of around 7 gigayears or younger, and they can be old, having 11 gigayears or older. In terms of metallicities, we know of some that are metal-rich and some that are metal-poor. And in terms of globular cluster richness, and by globular cluster richness, I mean the number of globular clusters that these galaxies hold, we know of some that are GC-poor and some that are GC-rich. The problem here is we don't know yet how to connect these observational properties with the theoretical formation scenarios that we have. And this is mostly because we don't have any statistically meaningful sample of UDGs to make this correlation. So this is where my PhD project comes off. We are trying to not use spectroscopy, but go to an metric band to try and recreate the spectrum of a galaxy. So here I'm showing DF44, which is one galaxy that Duncan talked about. Here we have 10 photometric bands for it, going from the optical to the mid-infrared. And our idea is to measure the flux here, plot it against the wavelength, and try to fit many spectra to it to find the best one. Well, the best one. Anyway, this way we can recover reliable stellar populations for them, hopefully. So we did this for 29 UDGs distributed across environments from the field to the cluster, and we used Prospector, which is a Bayesian spectral fitting code. So the first thing we did here was to compare the stellar populations that we were getting from SED fitting to the ones that we have from spectroscopy to see if we were recovering reliable stellar populations. So here I'm showing in the x-axis the age difference between the literature from spectroscopy and my ages from SED fitting, and in the y-axis the metallicities. And I have this information only for 4 galaxies on my sample, but what we find and what I want to draw your attention to is to the medium difference, which is shown by the red circle there, is that, well, within errors, we are consistent with 0, which is what we wanted, and we find that we have a difference of less than 1 gigayear in age and less than 0.2 dex in metallicity. So we are pretty consistent with 0, and we are happy with this result, so we can start to look into, well, what the whole sample has to tell us. So this is what I did. The first thing that we investigated was if the stellar populations depended on the environment that the galaxies reside in. So here I'm showing you the age metallicity plane, where the galaxies are split into field in green and cluster in red. And what you can see is that UDGs in the field are systematically younger than their cluster counterparts. If we look at this exact same plot, but this time color-coded by the globular cluster richness of the UDGs, what we see is that GC-poor UDGs, which are shown in blue, they are systematically more metal-rich and younger than the GC-rich counterparts. And this is something that we were not expecting, and we were quite surprised to find it. So what we did was to try and see, well, to explore more the separation in metallicity. And we did this by looking at the mass-metallicity relation. But before that, I would like to go into the mass-metallicity relation and try to explain like the different steps of it. So here is the mass-metallicity plane, and I'm overplotting in it 4 known mass-metallicity relations for galaxies. So in black and in purple are the mass-metallicity relations for dwarf galaxies. In yellow is the mass-metallicity relation for giant galaxies. And the dashed green line is the evolving mass-metallicity relation at a redshift of 2.2. So now that we are all familiar with this, I'm just going to overplot all of my data, and hopefully this is not too much. We have in gray here all of the literature data, and I want to draw your attention to my results, which are shown by squares here. And so the galaxies are again color-coded by GC poor in blue and GC rich in red. And what we see is that the GC poor UDGs, they are consistently more metal-rich. This is something that we already knew. And since they are more metal-rich, because of this, they are consistent with the dwarf mass metallicity relation. They have a smaller number of globular clusters. Yes, because of these two things, we conclude that they are likely puffed-up dwarfs. On the other hand, we have this population of GC-rich UDGs that they are not consistent with the dwarf mass metallicity relation. Instead, they are more consistent with the evolving mass metallicity relation at a redshift of 2.2. So they are consistent with early quenching. So these are galaxies that have a large number of globular clusters, and they are consistent with early quenching. So because of these properties, we believe that they are likely failed galaxies. So these are my main conclusions. With SED feeding, we are able to recover reliable stellar populations for UDGs, which opens up a new pathway to studying many UDGs across the field using just photometric bands. We have found a stellar population dependence both on environment and globular cluster richness, here shown, yes. And using the globular cluster richness separation on metallicity, we were able to come up with permission scenarios for these galaxies. So globular cluster poor UDGs, they are metal rich and they are younger. They are consistent with the mass metallicity relation for dwarf galaxies. And because of the combination of all of these properties, we believe that they are puffed up dwarfs. On the other hand, GC rich UDGs, they are metal poor and they are old. They are consistent with early quenching. And because of the combination of all of these properties, we believe that they are likely failed galaxies. Just to finalize, I only had time to talk about one of our works, but we have been using, within our group, globular clusters to understand UDGs for a long time now. And these are some of my other works that if you're interested in, please have a look. And as Duncan said, I just want to resonate, me and Joan again, and we are organizing a conference later in the year in Melbourne to talk about ultra-diffuse galaxies and about how we fit into ASTRO 3D, and we're really excited about it. So if you're interested in it, just come talk to me, and we will hopefully send an email soon about it. And yeah, that's it. Thank you.